Hello guys, once again welcome back to my channel FNHSO. I'm Faith and today I'm here with a new topic, and today's video is based on the topic from Standard 12 NCERT Chemistry, Chapter 12 Aldehydes, Ketones and Carboxylic Acids, Part 1. Unit 12 Aldehydes, Ketones and Carboxylic Acids. Objectives. After studying this unit, you will be able to write the common and IUPAC names of aldehydes, ketones, and carboxylic acids. Write the structures of the compounds containing functional groups, namely carbonyl and carboxyl group. Describe the important methods of preparation and reactions of these classes of compounds. Correlate physical properties and chemical reaction of aldehydes, ketones and carboxylic acids with their structures. Explain the mechanism of a few selected reactions of aldehydes and ketones. Understand various factors affecting the acidity of carboxylic acids and their reactions. Describe the uses of aldehydes, ketones, and carboxylic acids. In the previous unit, you have studied organic compounds with functional groups containing carbon-oxygen single bond. In this unit, we will study about the organic compounds containing carbon-oxygen double bond, called carbonyl groups, which is one of the most important functional groups in organic chemistry. In aldehydes, the carbonyl group is bonded to a carbon and hydrogen, while in ketones, it is bonded to two carbon atoms. The carbonyl compounds in which carbonyl group is bonded to oxygen are known as carboxylic acids and their derivatives, example esters and anhydrous. While in compounds where carbon is attached to nitrogen and to halogens are called amides and acyl halides respectively. The general formulas of these classes of compounds are given below. Aldehyde, ketone, carboxylic acid, acyl halide, in which this character X stands for halogens like iodine, fluorine, etc. and acyl anhydride. Esters, amides. Aldehydes, ketones, and carboxylic acids are widespread in plants and animal kingdom. They play an important role in biochemical processes of life. They add fragrance and flavor to nature, for example, vanillin from vanilla beans, salicylaldehyde from meadowsweet, and cinnamaldehyde from cinnamon have very pleasant fragrance. Vanillin, salicylaldehyde, cinnamaldehyde. They are used in many food products and pharmaceuticals to add flavors. Some of these families are manufactured for use as solvents, that is acetone, and for preparing materials like adhesives, paints, resins, perfumes, plastic, fabrics, etc. Nomenclature and structure of carbonyl group. Nomenclature. First one, aldehydes and ketones. Aldehydes and ketones are the simplest and most important carbonyl compounds. There are two systems of nomenclature of aldehydes and ketones. First one is common names. Aldehydes and ketones are often called by their common names instead of IUPAC names. The common names of most aldehyde are derived from the common names of the corresponding carboxylic acids. Refer section 12.6.1 by replacing the ending, that is, of acid with aldehyde. At the same time, the names reflect the Latin or Greek term for the original source of the acid or aldehyde. The location of the substituents in the carbon chain is indicated by Greek letters alpha, beta, gamma, delta, etc. The alpha carbon being the one directly linked to the aldehyde group, beta carbon the next, and so on. For example, acetaldehyde, benzaldehyde, and beta bromobutyraldehyde. In beta bromobutyraldehyde, we can see how the um, All the carbon atoms are named by giving alpha. The alpha carbon is linked to the aldehyde group, that is CHO, and the next one would be beta and gamma. The common names of ketones are derived by naming two alkyl or aryl groups bonded to the carbonyl group. The locations of substituents are indicated by Greek letters alpha, alpha dash, beta, beta dash, and so on, beginning with the carbon atoms next to the carbonyl group, indicating as alpha, alpha dash. Some ketones have historical common names. The simplest dimethyl ketone is called acetone. Alkyl phenyl ketones are usually named by adding the acyl group as prefix to phenone. For example, acetone, acetophenone, propiophenone, benzophenone. Second one is IUPAC names. The IUPAC name of open chain aliphatic aldehyde and ketones are derived from the name of the corresponding alkenes by replacing the ending E with al and 1 respectively. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of aldehyde group, while in case of ketones, the numbering begins from the end nearer to the carbonyl group. The substituents are prefixed in alphabetical order along with numerals indicating their position in the carbon chain. The same applies to cyclic ketones, where the carbonyl carbon is numbered 1 when the aldehyde group is attached to a ring. The suffix carbaldehyde is added after the full name of the cycloalkene. The numbering of the ring carbon atoms start from the carbon atom attached to the aldehyde group. The name of the simplest aromatic aldehyde carrying the aldehyde group on a benzene ring is benzene carbaldehyde. However, the common name benzaldehyde is also accepted by IUPAC. Other aromatic aldehydes are hence named as substituted benzaldehydes. Ethanol, 4-bromo-3-methyl-heptanol, 3-methyl-cyclopentanone, cyclohexane carbaldehyde, pent-2-enol, 1-phenyl-propan-1-on, 3-oxopentanol, 2,4-dimethyl-pentan-3-on, 4-nitrobenzene carbaldehyde or 4-nitrobenzaldehyde. This one is propane 1,2,3 tricarbaldehyde. The common and IUPAC names of some aldehydes and ketones are given here. Common and IUPAC names of some aldehydes and ketones. Structure, first commonly IUPAC name. First one, aldehydes. HCHO, formaldehyde, methanol. CH3CHO, which is acetaldehyde and ethanol. CH3 twice CHCHO, which is called the isobutyraldehyde, which is also 2-methylpropanol. Next one is H3C, benzene benzene ring CHO. That is gamma-methyl cyclohexane carbaldehyde, which is also 3-methyl cyclohexane carbaldehyde. CH3CH OCH3CHO, alpha methoxypropanaldehyde, which is 2-methoxypropanol. CH3 CH2 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 CHO, which is valeraldehyde, which is pentanol. CH2 double bond CH-CHO, acrolein, which is proper to NR. Next is benzene, CHO, that is thialdehyde, which is benzene. 1,2-dicarbaldehyde. Next one is benzene with CHO and Br, which is M-bromobenzaldehyde, which is in IUPAC name is 3-bromobenzene carbaldehyde or 3-bromobenzaldehyde. Next one is ketones. CH3CO, CH2, CH2, CH3. Methyl N-propyl ketone, which is pentane 2-O. CH3 twice CH, CO, CH, CH3 twice, which is diisopropyl ketone, which is 2,4-dimethyl pentane 3-O. Next is benzene with double bond O and CH3. Alpha methyl cyclohexanol, which is 2-methyl cyclohexanol. CH3 twice C double bonded CH, CO, CH3, which is methyl oxide, which is methyl penta 4-methyl penta 3N2-on. 12.1.2 Structure of the carbonyl group. The carbonyl carbon atom is sp2 hybridized and form 3 sigma bonds. The fourth valence electron of carbon remains in its p orbital and forms a pi bond with oxygen by overlap with p orbital of an oxygen in addition. The oxygen atom also has 2 non-bonding electron pairs. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane, and the pi electron cloud is above and below this plane. The bond angles are approximately 120 degrees as expected of a trigonal coplanar structure. Figure 12.11. This is the figure. The carbon-oxygen double bond is polarized due to higher electronegativity of oxygen related to carbon. Hence, the carbonyl carbon is an electrophilic Lewis acid and carbonyl oxygen a nucleophilic Lewis base center. Carbonyl compounds have substantial dipole moments and are polar than ethers. The high polarity of the carbonyl group is explained on the basis of resonance involving a neutral A and a dipolar B structures as shown over here. Preparation of aldehydes and ketones. Some important methods for the preparation of aldehydes and ketones are as follows. Preparation of aldehydes and ketones. First one, by oxidation of alcohols. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols respectively. Refer Unit 11, Class 12. Second one, by dehydrogenation of alcohols. This method is suitable for volatile alcohols and is of industrial application. In this method, alcohol vapors are passed over heavy metal catalyst, which is Ag or Cu. Primary and secondary alcohols give aldehydes and ketones respectively. Refer Unit 11, Class 12. Third one is from hydrocarbons. First one, by ozonolysis of alkenes. As we know, ozonolysis of alkenes followed by reaction with zinc, dust and water gives aldehyde. Ketones are a mixture of both depending on the substitution pattern of alkene. Refer Unit 13, Class 12. Second one, by hydration of alkynes. Addition of water to ethine in the presence of H2SO4 and HgSO4 gives acetaldehyde. All other alkynes gives ketones in this reaction. Refer Unit 13, Class 12. Next one is preparation of aldehydes. First one, from acyl chloride, acid chloride. Acyl chloride, which is acid chloride, is hydrogenated over catalyst palladium or barium sulfate. This reaction is called Rosenman reaction. This is the Rosenman reaction given here. Second one, from nitriles and esters. Okay. Nitriles are reduced to corresponding amines and stannous chloride in the presence of hydrochloric acid, which on hydrolysis give corresponding aldehyde. RCN plus SnCl2 plus HCl gives RCH double bond NH, which in presence of H3O plus gives RCHO. This reaction is called a Stephan reaction. Alternatively, nitriles are selectively reduced by diisobutyl aluminium hydride, which is dimethyl. Two amines followed by hydrolysis of aldehyde. RCN in the presence of ALH, which is BU double twice, and H2O gives RCHO. CH3 CH double bond CH CH2 CH2 CN in the presence of ALHIBU twice, and H2O gives CH3 CH double bond CH CH2 CH2 CHO. Similarly, esters are also reduced to aldehydes with dimethyl H. CH3 CH2 9 times attached to C double bond O C2H5 in the presence of dimethyl H and H2O gives CH3 CH2 and 9 times C double bond OH. Third one, from hydrocarbons. Aromatic aldehydes, benzaldehyde and its derivatives are prepared from aromatic hydrocarbons by the following method. First one, by oxidation of methyl benzene. Strong oxidizing agents oxidize toluene and its derivatives to benzoic acids. However, it is possible to stop the oxidation at the aldehyde stage with suitable reagents that convert the methyl group to an intermediate that is difficult to oxidize further. The following methods are used for this purpose. First one, use of chromyl chloride, which is CrO2Cl2. Chromyl chloride oxidizes methyl group to a chromium complex, which on hydrolysis gives corresponding benzaldehyde. First one, toluene plus CrO2Cl2 in the presence of CS2 gives chromium complex, which in the presence of H2O plus gives benzaldehyde. This reaction is called Ettard reaction. The second one is use of chromium oxide CrO3. Toluene or substituted toluene is converted to benzaldehyde diacetate, or treating with chromic oxide in acetic anhydride. The benzaldehyde diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. That is, toluene plus CrO3 plus CH3CO twice O in the presence of with this 273 to 283 Kelvin gives benzene OCO CH2 twice, CH3 twice in the presence of H3O plus and heat gives benzaldehyde by side chain chlorination followed by hydrolysis. Side chain chlorination of toluene gives benzal chloride, which on hydrolysis gives benzaldehyde. This is a commercial method of manufacture of benzaldehyde. Toluene in the presence of Cl2 or HNO gives benzal chloride in the presence of 373 Kelvin and H2O gives benzaldehyde. Next by Cutterman-Koch reaction. When benzene or its derivatives is treated with carbon monoxide and hydrogen chloride in the presence of anhydrous aluminium chloride or cuprous chloride, it gives benzaldehyde or substituted benzaldehyde. Benzene in the presence of concentrated HCl and anhydrous aluminium chloride or cuprous chloride gives benzaldehyde. This reaction is known as Cutterman-Koch reaction. Next one, preparation of ketones from acyl chlorides. Treatment of acyl chlorides with dialkyl cadmium prepared by the reaction of cadmium chloride with Grignard reagents gives ketones. 2R-MgX plus CdCl2 gives R2CD plus 2MgXCl. 2R-C double bond OCl plus R2CD gives 2R-C double bond OR plus CdCl2. Second one, from nitriles. Treating a nitrile with Grignard reagent followed by hydrolysis yields a ketone. CH3 CH2 single bond C triple bond N plus C6H5MgBr, which in the presence of either gives CH3 CH2 single bond C triple bond N MgBr and single bond C6H5. In the presence of H3O plus gives C2H5 with single bond C attached to double bond O and single bond C6H5, which is propiophenone 1-phenyl propanone. Third one is from benzene or substituted benzenes. When benzenes or substituted benzenes is treated with acid chloride in the presence of anhydrous aluminium chloride, it affords the corresponding ketone. This reaction is known as Friedel-Crafts acylation reaction. Benzene plus Ar or R C double bond O Cl in the presence of anhydrous aluminium chloride gives benzene single bond C double bond O single bond Ar or R. Okay guys, that's the end of this video, and I hope you guys like this video. If you guys like this video, don't forget to like, share, and comment. And if you haven't subscribed yet, please subscribe and press the notification icon so that you will get the notification when I upload the new video. So thank you, take care, bye.